All right, greetings everyone. Welcome to the third and final video for section 7.4 and the end of chapter 7, which is crazy. All right, so we've been looking at changing midlines in the last couple of videos. Let's look now at what happens if we have a changing amplitude. So changing amplitude comes up in the context of what we call damped harmonic motion. Which is basically motion exhibited by springs subjected to friction. And it follows a model of the form f of t equals a times b to the t times sine of bt plus k, or cosine of bt plus k. Or we can also write it using continuous growth as f of t equals a times e to the rt sine bt plus k. And in this case, I would say that you can use either of these formulas for the types of problems. The one that I'm going to demonstrate most is this one here. So that's the one I'll expect you to know. But let's also look at how this relates, this property of springs relates to trig functions and what's going on here. So to see this, what we'll do is go to a video that I have here, which is this one. And notice here we have a spring, and in this case it's starting at what is called its natural length. Okay, so it hasn't been stretched or compressed at all. And notice, follow this little ball here as the spring compresses and then stretches. So it gets shorter and then back to its original length, and then it gets longer and then goes back up and repeats the pattern. Now, what you might imagine is if there's friction working on this spring, or if we're working in the real world on this spring, it's not going to continue to oscillate at the same rate or at the same lengths, right? Generally what happens is if we stretch out a spring, at first it'll oscillate a lot in each direction, but then as over time it'll start to oscillate less, right? So unfortunately this video doesn't show that, but that's what would happen. So let's go back to this and look at an example. So let's say that we have a spring with a natural length of 40 centimeters that is pulled down 8 centimeters and released. So, oops, sorry about that. So our spring looks like this. Okay, and yes, you can laugh at my spring if you want. So normally it's 40 centimeters in length if it hasn't been stretched or compressed. That's what the natural length means. But in this case, this one has been stretched an additional 8 centimeters. Okay. So that's how we're starting. And so we need to write an equation to describe this, although I should read the rest of the problem. It oscillates twice a second. Its amplitude decreases, by 30% each section due to friction. So we need to find a formula that models the length of the spring t seconds after it's being released. Now, notice in this case that the spring is starting elongated, right? It's been stretched out. So it's not starting its natural length, which tells us it's not starting at the midline, because remember on that video we saw when it's at the midline. That's when it was at its natural length. So it's actually been stretched out, so it'll be longer than normal, which you can imagine if we were graphing what this would look like. Okay, if our average or natural length is right here, that's at 40 centimeters. It's starting stretched out, which means it's going to be longer, which just means it's starting off the midline up here, right? So above that. So it looks like our function over time would look something like this, which looks to be cosine. So the function we'll write, I'll call L of t for length. It'd be of the form A, or excuse me, not capital A anyways. Following from that previous slide, A times b to the t times cosine of capital B t plus k. And let's think about what each of these things will be. Well, the a times b to the t, that describes the oscillation, right? Or the length that the length of the length of the spring changes every second. And we notice at first of all, the length of the spring is 8 centimeters longer. So our amplitude begins at 8 centimeters. So that would be the value for lowercase a, times, remember the value for b comes from 1 plus r. And we're told here that the amplitude is decreasing by 30% each second. So we know that 0.3 is 30%, but it's decreasing here. So rather than doing 1 plus r, we'll actually do 1 minus r, which gives us 0.7. So we should have 8 times 0.7 to the t here. Remember, to find the value for b, we need to know the period, which the period for this function, well, notice we're told that the spring oscillates twice a second, which means how long does it take to do one full oscillation? That's right, that would be a half a second, right? If it's doing it twice a second, that means a half a second is a single period. So we can use that to find b. So b will be 2 pi divided by that period, which is 1/2, which if we divide that, it'll be 2 pi over 1 times 2 over 1, which will give us 4 pi for the value for capital B. And then the value for k, that's going to be the midline, kind of the value that the function is oscillating above or below, which, as we said earlier, would be the natural length of the spring, which is 40 centimeters. So it looks like now we have all the information for our equation. So it'd be L of t equals a times 0.7 to the t times cosine of 4 pi t plus 40. Okay. And there we go. That would be our equation. Now, you might be wondering what this might look like, especially because the example I had in the video didn't quite show us. Let's take a look at what happens if we graph this. So go here, see I've got it plugged in. I'm going to change something, so hopefully it'll show us graphing. And when we graph it, notice we kind of see what we expected at first. There's big oscillations. The spring is first pulled back, but then over time, those oscillations are getting smaller and smaller as time moves on, right? And the amplitude is becoming less and less, which hopefully again makes sense because as friction and gravity act on the spring, it'll oscillate less over time. All right, let's take a look at another example. Okay, so this time our spring has a natural length of 50 centimeters. Oops, sorry again. So before it's pulled back, the length is 50 centimeters. And then it's stretched out an additional 16 centimeters. And the spring oscillates 3 times a second, which helps us know the period then. The period will be, if it's oscillating 3 times a second, that means a single oscillation takes 1/3 of a second. You can use that to help us find the value for capital B, which would be 2 pi divided by 1/3, which would be 2 pi over 1 times 3 over 1. So it looks like we get 6 pi there. And then we're also told that after 3 seconds, the amplitude has decreased to 2 centimeters. So in this case, if you think about our equation for the amplitude, a times b to the t, we know the initial value for the amplitude, which is 16, but they don't tell us anything about b this time. They didn't tell us how much it's increasing or decreasing over time, but they did tell us that after 3 seconds, the amplitude is decreased to 2 centimeters. So we can use that information to set up an equation where we would have 2 centimeters being the length of, or excuse me, the amplitude of the spring after 3 seconds will equal 16 times b cubed. We can solve for b here, so we can divide by 16 on both sides. When we do that, we'll end up with 2 over 16, or 1/8, equals b cubed. Can then solve for b by taking the cubed root on both sides. You can plug that in your calculator, or you can think about, because we have a cubed root of a fraction here, we can do the cubed root of the top over the cubed root of the bottom. Cubed root of 1 is 1, because 1 times 1 times 1 equals 1. Cubed root of 8 is 2, because 2 times 2 times 2 gives us 8. So there's our value for b. So now we know that the a times b to the t will have the form 16 times 1/2 to the t. I've got the value for b. The other thing we need is the value for k. For our midline, which, as we talked about in the last problem, is the natural length of the spring, so the 50 centimeters. And again, we're starting with the spring elongated. So we're starting off the midline, or off the natural length. And again, we're starting above it this time, so it's going to be positive cosine. So our function should look like 16 times 1/2 to the t times cosine of 6 pi t plus 50. There's our equation. Cool. Now, you may be wondering, why did we only do exponential forms for the changing amplitude? Because we did exponential, linear, and looked at quadratic for changing midlines. And this next slide kind of shows that. We could have it, but notice what will happen over time is we'll actually see an increase and a decrease in the amplitude, or a decrease and an increase in this case. So notice the amplitude's going down, but then it goes back up, right? Which, especially if we're modeling the oscillations of a spring, that won't work for us. Now, it might work in some other circumstances, though. We can also look at, and this is cool, sinusoidal amplitude. So notice here we have a sine function. What's in the place of the amplitude is another sine function, right? So here you see the amplitude actually changing according to a sine function, which is kind of neat. So you could experiment on your calculators or Desmos with other types of amplitudes and see what you get. All right, that's it for section 7.4. Thanks for watching.